Section 6.4, solving trigonometric equations involving identities. So today we're going to solve all trigonometric equations again within certain domains, but we're going to solve obviously more complex trig equations that involve identities. So the first example we're given is sine of 2x plus sine of x is equal to 0. The whole idea with solving equations is we want to break down our equation so it's generally in terms of just sine of x or cos of x. Look at this equation. I have a sine of 2x and a sine of x. Sine of 2x is a completely different trig ratio than sine of x. So it's like trying to solve an a plus a b equals 0. It would be impossible to solve. We have two different variables. So what I'm going to do is I want to change this sine of 2x using my double angle identities so that this is in a single angle as opposed to a double angle. So I'm going to change sine of 2x. I'm going to replace this with using my double angle identities is equivalent to 2 sine of x cos of x, and then I have plus sine of x equals 0. So now that my equation is in terms of sine and cos, now I'm ready to start to solve this equation. Look at this equation. I can factor out a sine of x, and I'm left with 2 cos of x plus 1. So now that my equation's in factored form, I can take both of these factors, make them equal to 0, and solve for x. So I have a sine of x equals 0. And then I have a 2 cos is going to equal negative 1, so cos of x is equal to a negative 1/2. And so now I'm looking for the ratios when sine of x is equal to 0, or sorry, looking for the angles when the ratio value is 0 for sine of x and when the ratio value is a negative 1/2. And we're working in the domain 0 to 2 pi. So when is sine of x equal to 0? Well, my solutions would be 0, pi, and 2 pi. So this would be one expression. And then my second part, when is cos of x equal to a negative 1/2? So looking on my unit circle, I would get 2 pi over 3 and 4 pi over 3. So this equation would have 5 solutions. All right, moving on to question B, 6 sine squared x equals cos of x plus 4. So again, when I look at this, this is a quadratic equation with a cos of x, so I'm going to somehow, I either want to sine of x or cos of x generally. I can't replace cos of x with anything. We're kind of stuck with that. So we're going to replace the sine of x or sine squared x. This is our Pythagoras identity. Can be replaced with a 1 minus cos squared x. Okay, I'm also going to make my equation equal to 0 because I know I'm going to end up with a quadratic equation that I have to solve for 0 eventually. So we'll leave this as is right now, and then we'll see which side we're going to move everything to after I've in my brackets here. Okay, so after expanding the 6 brackets, I get a 6 minus 6 cos squared x. This is a quadratic equation that we're going to make equal to 0, but rather than moving these values to this side, I'm going to decide to move these over to the positive a value. So this is going to be 0 equals 6 cos squared x plus cos of x. If I move the plus 6 over here, this is going to become a minus 2. All right, so now we are ready to solve this or factor this quadratic equation. So I'm looking for the factors of 6, factors of 2. When added together, I'm going to get a plus 1. Okay, and so when we factor this, we end up with factors of cos of x, 3 cos of x plus 2, and 2 cos of x minus 1. So just to double check, this would give me a negative 3 cos of x. This would give me a plus 4 of x. If I collect those together, I'll get a plus 1. So this is still equal to 0. So then I have expressions of cos of x equals negative 2/3 and cos of x a positive 1/2. Okay. So we are now looking for the solutions on our unit circle between negative 2 pi and positive 2 pi. So rotating around from 0 to negative 2 pi, I can look up this ratio on my unit circle. So these solutions I'm going to give an exact values. So it should be a negative 5 pi over 3, a negative pi over 3, a positive pi over 3, and a positive 5 pi over 3. So if you wanted to just double look at that on the unit circle, right, I'm rotating in this direction. So from 0 to 2 pi, I'm looking for when cos of theta is equal to 1/2. Well, this would be my first position, which would be a negative pi over 3. And my next position would be here, which would be a negative 5 pi over 3. And then if I rotate from 0 to 2 pi, I get positive and a positive 5 pi over 3. So that's how we come up with those values. This next part is I cannot look up negative 2/3 on my unit circle, so I have to use my calculator and my cast rule to come up with my solutions. So the first thing I'm going to do is find my reference angle of x by taking second cos. I should be in radian mode. Second cos of a positive 2/3. So you always leave out the negative value, and I get a reference angle of 0.4. Okay, so now using my cast rule and my reference angle, I'm going to determine, I'm going to rotate the same way. So I'm going to go from 0 to 2 pi in this direction. I'm going to look under my coordinate, using my cast rule, figure out which quadrants cosine is going to be negative, which would be in quadrants 2 and 3. So my first solution, I guess, would be this farthest solution of pi. So x equals, here I'm going to take a pi plus 0.84. So maybe we'll just store this answer in my calculator. So I constantly have it. So my first, if I take pi plus that angle, I get 3.98, but that should be a negative 3.98. And then my second solution would be here, which I'd want to take pi minus that angle, which is negative 2.20. And now I want to rotate in the positive direction. Well, when I rotate in the positive direction, my angles are still going to occur in quadrants 2 and 3. We're just rotating in the positive. So here, this would be pi minus my reference angle. So when I do that, I get a positive 2.30. And when I go terminal arm, I'm going to go pi plus that angle, which would be a positive 3.98. So all of my solutions for this entire equation, I should get 8 solutions here that are exact values, and then the second set which are rounded values. Okay, so moving on to question C. We're given sine squared x is equal to tangent of x times cos of x. So what we want to do is, again, we have lots happening here. We have a sine x, we also have a tangent of x. We want to, again, use identities to somehow simplify this before we begin. We also, in this case, would have to talk about non-permissible values. So before we start, we wouldn't have any non-permissible values for sine or cos, but we definitely do for tangent. So our non-permissible values, tangent is the same as sine over cos. So we know that cos of x cannot equal 0. So on our unit circles, when does cos of x equal 0? Well, that would be at pi over 2 and 3 pi over 2, and then every pi after that. So when we're solving an equation, you always have to consider your non-permissible values. So in this case, our non-permissible values would be x cannot equal pi over 2 plus every pi n after that, where n belongs to our integers. All right, so now we're ready to solve this equation. Before we begin to solve, we can simplify the right side of our equation by rewriting tan as sine over cos. And so what happens is our coses actually just cancel each other out. Because I'm working with a quadratic equation equal to 0, so now I'm going to move this sine of x to the other side of my equation. Now I can factor out a sine of x. And we're left with sine of x times sine of x minus 1. Before we go any further, I just noticing that my domain should be 0 to 360, so let's just change our non-permissible values. This should be a 9 degree and plus every 180 n. Okay, so now we're going to sine of x is equal to 0. We also have a sine of x is going to equal 1. So my solutions for when sine of x is equal to 0 would be at 0 degrees, 180, and 360. My solutions for when sine of x is equal to 1 is going to occur at 90 degrees. So now we want to double check with our non-permissible values to make sure none of these fall within our non-permissible values. And it does. Their 90 degree is actually a non-permissible value. So x cannot equal 90 degrees. So this is, we call like an extraneous root. Or non-permissible value. So my solution would be 0, 180, and 360. All right, question D. Given cos of 2x is equal to root cos of x minus 1, give the general solutions in radians. So we're just looking for a general solution here. Again, what we'd want to do is this is a single angle of x and this is a double angle, so we'd want to replace this with our double angle identities. And so cos of 2x, remember there's like 3 identities you can kind of choose from. I am going to choose the one of just cos squared x minus 1, just so that I'm only working in terms of cos squared x, right? So these are identities. I'm going to choose this one to replace it with, because I don't want to work in sine and cos, and same thing here. This gives me an expression sine and cosine. So I'm going to choose to replace 2 sine of x, cos squared x minus 1 equals root 3 cos of x. All right, so from this point, we're working with a quadratic equation again. So generally, we need to make our equation equal to 0. So I'm going to move everything over to the left side of the equation. This is going to become a minus root cos of x. When I move this plus 1 to the other side, these ones end up just canceling each other, and we get a value equals 0. Now we can factor out a cos of x as a common factor, and I'm left with cos of x minus a root 3 equals 0. My solutions are going to be cos of x equals 0 and cos of x is equal to a root 3 over 2. We didn't have any non-permissible values for this question because there are no non-permissible values for cos of x. So we now are going to look at these solutions and then get our general solution. So when is cos of x equal to 0? Well, that's going to occur at pi over 2 and 3 pi over 2. And when is cos of x equal to root 3 over 2? It would be at pi over 6 and 11 pi over 6. So our general solution. These two angles are related to each other within 1 pi radians each time, so we can kind of combine these together. These unfortunately are not, so I'd have to add a 2 pi every time to this solution and a 2 pi to this solution each time. So my general solution is going to be all three of these solutions, pi over 2 plus n pi, pi over 6 plus 2n pi, and 11 pi over 6 plus 2n pi. And then where all of these, where n belongs to our integers. So this would represent our general solution. Okay. And then finally, we are our last question. We're given 2 cosecant squared of x plus cosecant of x minus 1 equals 0. Give the general solution in degrees now. So before we begin, we need to talk about our non-permissible values in this case, because cosecant of x is equivalent to 1 over sine. And so when is sine of x? Sine of x cannot equal 0. So when does sine of x actually equal 0? This would be at 0, 180, 360, and so on. So my non-permissible values cannot equal 180 degrees n, where n belongs to the integers. Okay, so we need to keep that in mind when we're solving this equation. If we get anything that falls within those values, then they're not going to be a solution for the equation. All right, so this is a fairly straightforward factoring question. It's already equal to 0. I'm going to simply factor this equation. So the factors of 2 and 1 that add positive 1 in the middle, right, would be, so my factor should be 2 cosecant of x, cosecant of x. I need to multiply the 2 by a 1. The only factors of 1 have to be 1 and 1. I want this to be a plus 1, so the plus 1 would go here to make it a plus 2, and a minus 1 to go here to make it a negative 1. If I add those together, I'm going to get a plus 1. This is still equal to 0. So now if I solve for cosecant of x, I'm going to get 1/2. And here I'm going to get a cosecant of x is equal to a negative. All right, well, cosecant is the reciprocal of sine, so now I'm going to change this to a sine ratio by reciprocating my values. And when is sine of x equal to a 2? Well, that's impossible. Remember, our sine ratio always has to be within -1 for it to have a solution. So no solution. And when is sine of x equal to a -1? The only time it's equal to a -1 is at the 270 degree mark, which does not fall in with my non-permissible values. So my general solution, there's only going to be one of them, is x equals 270 degrees plus 360 degrees n. I want to add a full rotation to this each time, where n belongs to my integers. Right, and that is solving more complex trig equations.